So cosmic potential energy, we can't use MGH in outer space. Nick, why did we say you can't? G is changing. So I'm going to go to a graphical workaround. We're going to start out by recalling that the area under a force versus distance graph, we said that was equal to work. But I'm going to be even more specific now. So if you could label this graph with a force versus distance, and let's put kind of a generic, there's my graph. But I'd like you to do one more step. I'd like you right around here to put a random point little a, and right here to put a random point little b. And then go d d d d d d d d d d d d d d d d d d, and kind of color in or shade in that area there. Now that area is not only how much work. If I wanted to be really fussy, this area equals the work needed to move from A to B. This is how much work, how much energy it took to move this mystery object from A to B. I also noticed, Lorenzo, that as I moved it, I had to push harder and harder and harder. So this might even be not just pushing something uphill, but maybe the hill's getting steeper. I don't know, but it took work. We're going to use the same argument for gravitational force and distance r from the planet. So instead of force versus distance, it's going to be Fg and r. Don't write this next bit down, just kind of look up. You know that the equation for the force of gravity is that there. What I want you to notice is that if I'm talking about the relationship between gravity and radius, it's going to be 1 over r squared. I think in pre-calc, and most of you in pre-calc, you've done the reciprocal function. You did the reciprocal transformation. This is going to be the reciprocal of a parabola. And you might have actually done that. I'm just going to do a rough sketch. I'm going to tell you that if I graph the force of gravity versus radius, it looks kind of like this. It's a curve. And again, I'm going to put a random point A and another location B. And then I'm going to go D, 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 color, 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 color. This area is the work needed to lift, because we're going against the force of gravity. Instead of moving, I'll call it lifting an object from A to B. This is the work needed to lift an object from location A to location B inside this particular gravitational field. Bit of a problem here, Gabe. I don't have a formula for the area of that shape. If it was a lovely triangle, I can handle it, but this is a curvy thing. Who's in calculus? Okay, those that are in calculus, you've learned that the derivative finds you slopes of curves. There's another process that you'll learn probably around May, and it finds you areas under curves. Calculus was invented for two reasons: to find the slope of a curve and to find the area underneath the curve. So you'll get there. But you haven't got there yet, so I'm going to have to do a non-calculus, fast-talking, technically not correct, but it gets us to the right location workaround. Let's be even more specific. Again, let's put Fg. Let's put R. But this time, this force is going to be the force of gravity from the Earth, from our home. As a shape, it's still going to look like this. But now, instead of putting a random point A and a random point B, I'm going to put a point right about there, and that's going to be the radius of the Earth. This is where the Earth's surface is. The center of the Earth would be right on the y-axis, but I don't care about that. And here, this might be our orbital radius that we want to get to. This area here is the work, the amount of energy required to lift a satellite, a rocket, some object from Earth's surface to an orbital radius. Now, all this is potential energy. This would not stay in orbit because we haven't given it any kinetic energy yet. All this asks, Justin, this graph would say, how much rocket fuel do you need just to get it to the right height? Then you'll need to turn it sideways and fire the rocket some more to give it the right kinetic energy to stay up there. We're not going to deal with that just yet. We'll get there later on in the lesson. So this is how much work it would take to lift something up, not to put it in orbit yet, just to get it to the right height so that it can stay once in orbit once we give it the correct orbital speed. Got the argument? The question is, again, how do you find the area of that curvy thing? Calculus, which most of you don't know. So I'm going to do some fast talking here. This technically isn't the correct derivation, but it gets us to the right answer, so we'll live with it. Since work equals force times distance, we can say that work equals the force of gravity times r, force, times distance. We can say that it's going to be big G, big M, little m, over r squared times r. Oh, what? R cubed? I don't think so. I don't have an equal sign here. I think actually instead one of the r's, yeah, one of the r's cancels. Now instead of work, I'm going to be even more specific. I'm going to tell you what this actually is the amount of potential energy required. Put an equal sign. Do me a favor, leave a space and then write big G, big M, little m over r. This is cosmic potential energy. No, it's not. This is incorrect. Now I'll make it correct. Everybody look up. It's negative. What? Yeah. The negative doesn't pop out of the math. Why is it negative? Who are my calculus students? Okay. It's negative because force is the derivative of energy. If you take the derivative with respect to r, this would be actually a little r to the negative 1. The negative 1 would move to the front, making it negative. You would subtract 1 from the exponent, give you r to the negative 2, move it to the bottom, and you'd get big G, big M, little m over r squared. But to make this one positive, we have to have a negative here, so the negative times the negative equals positive. Hang on, let me pause the video, whoever that is. Students, I saw a few of them. Oh, yeah. If you haven't figured it out, those of you that are in calculus, derivatives in physics, everything's related. One thing's a derivative of another thing of another thing. They're very related. Non-calculus students. Okay. We want to define where there is no potential energy. Where would you have no potential energy? I'm going to stand up and move away from the speakers. Sorry for those of you watching on YouTube. So here's my satellite. And I'd like you to imagine that the Earth is right here. If I lifted the satellite right to here, it will fall. Because it will fall, it has potential energy. If I lifted the satellite away from the Earth this far, it will still fall, but gravity is getting weaker. However, Nick, If I go all the way out to the edge of the universe, infinitely far from Earth, where there is no gravity acting on me, when I let go of the satellite, it will float. It will stay there. Because it won't fall, it has no potential energy. The reason I know that is, since there's no potential energy, there's nothing changing to kinetic energy. It's going to just stay there. So where do I have zero potential energy? Out at infinity. We did that on purpose because to try and define it in terms of Earth, that's very egocentric, Gabe. We're going cosmic here, and Earth is not the center of the universe. So we said, let's define zero to be all the way out at the edge of the universe, because that is where you would have no potential energy. So where do I have zero potential energy? All the way out at the edge of the universe. Now, to get there, I would have to add energy to get there, because as I'm moving the satellite away from the Earth is constantly tugging on it. Okay? You okay? Yeah. Okay. To get there, I would need to move away from Earth, and I would have to add energy. Is that the argument? If I have to add energy, that means right now I have less energy than out at infinity. How much energy do I have out at infinity as a number exactly? 0. What numbers are less than 0? Okay. So we're going to define zero energy to be out at infinity. Here's what I wrote. Out at infinity, at the edge of the universe, an object would have no potential energy because it's not being affected by any gravitational field. It can't fall. If our height is less than infinity, we have less potential energy. What numbers are less than 0? Negative. In fact, we use the phrase relative to 0 at infinity. Often you'll see me abbreviate R, T, Z, A, I. That's a hint. If you see that in a question, I'm saying use the cosmic potential energy equation. Now, do me a favor. I should have put a big box here, and I didn't. Can you draw a box around that? That's our equation of the day. It's on your formula sheet. Negative big G, big M, little m over R. Now, there is plenty of opportunity to make silly mistakes. Because the force equation is an R squared, it's easy to put a squared in there because you're not paying attention. Don't. It's easy to miss the negative. Don't. And it's easy to get intimidated because it's going to look really weird because you're going to be thinking, wait a minute, I'm going to get a negative answer. As long as you are careful, Chloe, you shouldn't. I'll show you what I mean. I like example 1. I like example 1. I like example 1. Example 1 is a nice question. A mass is released from a height of 6,300 kilometers. Nice try, kilometers. 6,300 times 1,000. You're going to notice in the homework, I will often give you distances in kilometers, and that's because I'm trying to use the same language as the industry does, but in physics, we use meters. So just make sure you're paying attention. 6.3 times 10 to the 6th. Meters above the Earth. How fast will it be going when it hits the ground if we ignore air resistance? Chloe, what's this question asking us to find? Speed. Any suggestions on how I might do this? My block A is I had somebody have the aha moment, so I'll just pause. Can you? What would I use? What? Conservation of energy. Is there a change in height? Yes. Is there a change in speed? Yes. Look up, look up, look up. Is there a yucky, curvy force? This is a job for conservation of energy. I think previously I had said if there's a yucky, curvy path, there's a yucky, curvy force. We're going to use conservation of energy. So, K-E initial plus P-E initial. Write small, trust me. K-E final plus P-E final. Graham, put your calculator down. Nobody goes to the calculator until I say, for a reason. You'll see why, not to be mean. Are any of these 0? I think we're going to say, since it says released, that kinetic initial is 0. Unfortunately, final potential is not going to be 0. 0 would be all the way out in infinity. Final potential is not going to be 0. Potential energy. Don't write this down. Why would that be wrong? Yeah, we're cosmic now. So I have to use our new cosmic potential energy, which is negative big G, big M, little m over R initial equals a half mv final squared. That one hasn't changed. Plus negative big G, big M, little m over R final. Chloe, what are we trying to find? Don't try and get the v by itself. This is where my love of getting something by itself is stupid. Don't even try. Instead, Chloe, what I'm going to do, I'm going to plus this to that side, first of all. I'll get negative big G, big M, little m over R initial plus big G, big M, little m over R final. That equals a half mv final squared. Oh, I noticed something else. I could have done it on the previous line. I didn't because I was not paying attention. What else could I have done now or on the previous line? So it turns out the speed is not affected by the mass. The damage is affected by the mass, how much damage it does when it hits the ground. Oh, heck yeah. But in terms of how fast, if we're ignoring air resistance, what I'm going to do, I'm going to turn this into a single number. Then I'll times by 2 square root. Okay, Chloe? So don't try and get the v by itself. Okay, so let's plug and chug carefully. No calculators yet, please don't. Negative. Chloe, what's big G? Good. What's big M? Mass of the Earth. And our initial, we're 6.3 times 10 to the 6th meters above the Earth. So here's the Earth. We are 6.3 times 10 to the 6th meters above the Earth. I need that distance. How can I figure out that distance? Add it to, so down here, I'm going to write 6.3 times 10 to the 6th plus 6.38 times 10 to the 6th. And now Mr. Dueck is going to get cleverly lazy. This is why I said no going to your calculator yet. Chloe, the next thing I would write is a plus sign. Then what would I write? Don't write it, just tell me. More specific? Even more specific, isn't that the same thing as I have right there? I swear to you, I'm going to tell all of you, just put a ditto mark there, times. You've seen those used before, little quotation marks. And then what would I write, Chloe? Would I write the same 5.9? Then put a ditto mark there. Save yourself the writing, because it's the same thing. All over, what will be on the bottom here? Our final, which is the surface of the Earth, which I think is just going to be the 6.38 times 10 to the 6th. That's going to equal 0.5 v squared. A half v squared, because the m's cancel. You okay with that, Kimia? I want to try and come up with a way that saves you typing and reduces error. So here's what I'm going to say. Every one of you, pick up your calculator. Now you can, Graham. But only type in the first term. Type in the negative 6.67, scientific notation, negative 11, times 5.98, scientific notation, 24, divided by, I'll have to put the bottom in brackets, 6.3, scientific notation 6, plus 6.38, scientific notation 6. And hit equals. Don't type in the second term. Hit equals. Little rule of thumb, by the way, when you're talking potential energies for satellites and things, they're often in the 10 to the 9th or 10 to the 10th range. Oh, here, I got that. Is that right? You get negative 314,563,09.15. I'm going to write negative 314,563, and then I'll round off. The 3 is a nice place to round off because there's a 0 right there. So I'm just going to go negative 314,563 and 2 zeros. Negative 314,563 and 2 zeros. Plus. Have I gone on the occasional... Maggie, could you shut the door actually for me? Have I gone on the occasional calculator rant? This is why. Stop, Kimia. Backspace. Bring back the previous line. Do that. Because it seems to me, Kimia, all I need to do is delete the negative and delete the 6.3 times 10 to the 6th, and I'm done typing the second expression. So if you don't know how to backspace, hit me up later. You want to figure it out. This both reduces the amount of typing, but it also reduces the likelihood of a typo. Jacob, as long as you're fearsomely careful the first time you type it in, just backspace and ditto marks, and you'll get for the second term 625181818181818. Now there's a decimal there, and I'm pretty sure it's 18 repeating off the screen, and it's rounded off that 18 to a 2. I'm going to write it as 62518 and 3 zeros. I usually go to 5 or 6 sig figs, and that gives me safety to 3 sig figs in the end. What did I say it was? 6251830. 6251812 That equals 0.5 v squared. I have run out of room. You might still have more. But now what I'm going to do, Chloe, is just add these together. So I'm going to type negative 3145630 plus haha answer button. Less typing. When I do that, I get 3106188.82. Chloe, how would I get the v by itself now? Or divide by 0.5, and then I'll divide by 0.5, square root. That's right, it is 7,880. That is, I've tried a bunch of different methods, Grace. Using ditto marks and backspacing on your calculator is the best combination of, oh my goodness, I just have to do a lot of complicated typing, but I can make my life easier if I can. Okay. So this will be the physics of the asteroid impacts. I like example 2, I like example 2, I like example 2. Example 2 is a nice question. Trevor, what's example 2 asking me to find? Work. Oh, don't write this down. Why can't I go like this? Force of gravity times distance. Ah! Rats. What does it want me to find? Work? Hey, is there an equation for work that refers to work in terms of energies? That would be useful. And if so, which equation is that? So work is equal to, it's not kinetic energy plus potential energy. It's never said that. You read it incorrectly. I'm sorry, I got a snap. Aren't there triangles in front of everything? Oh, that's a huge difference. Sorry, what is it? Change in potential plus change in kinetic, or change in kinetic plus change in potential? Trevor, what word did I underline? And do me a favor, all of you, do you see the word orbit anywhere in this question? So this is not figuring out how much work to put something in orbit. All we're asking is how much energy, how much rocket fuel, how much work will it take just to get it to the right height? It's going to come crashing back down. Once we get it to the right height, and we'll do this in the next question, we'll also ask, okay, how much kinetic energy do I need to give it to keep it in orbit, to keep it, give it the V-orb? So that's why I underlined the word lifting. We're not putting this in orbit. This is just how much rocket fuel, how much work, how much energy, just to get it up there. So I'm going to assume in this question, because of the word lifting, because it doesn't say the word orbit, that we're starting and ending at rest. What's change in anything, Trevor, my friend? So the work is going to be mg, don't write this down, h final. Why can't I write mgh final minus mgh initial? We're going cosmic. Ugh. It's going to be our new equation. Negative big G, big M, little m over R final minus negative big G, big M, little m over R initial. Final minus initial. Now you do notice in the middle we get a minus minus, which is a, and that's good because we do want to end up with a positive answer. It should take work to lift something up there, and that's what's going to give us that. Do the little m's cancel this time? No, and that makes sense. It should take more fuel to put the space shuttle up there than it would take to put a little tiny satellite up there. It should take more work. So the m's shouldn't cancel here. All there is for it now is lots of writing and typing. The work is going to be negative. Trevor, what's big G? 6.67 times 10 to the negative 11, you say? What's the big M, mass of the Earth? Now, read the questions carefully, by the way. I think in the homework, once or twice, I go to the moon just for giggles. Make sure then you use the mass of the moon. It's also on your sheet. But here we're on the Earth, so 5.98 times 10 to what, Trevor? Good. And then little m, 1200 all over. First of all, that 1.2 times 10 to the 7th, is it in meters? Is it a radius or is it a height? Okay, so that means I've given you that distance. We want that distance. I'm going to have to add the radius of the Earth. On the bottom of the first fraction, it's going to be the height plus the radius of the Earth. Then there's a minus minus, Trevor, which is a... Are you positive? Big G, ditto mark, times big M, ditto mark, times little m, ditto mark. All of this is also about the only way that I can fit this on one line. Otherwise, and as soon as I go to multiple lines, that's when I also start making dumb mistakes, Maggie. I've learned that about me, so I'm trying to keep this vaguely organized. What's our initial? The surface of the Earth is where we're starting. So 6.38 times 10 to the 6th. We're going to, again, Kimia, do one term at a time, hit equals, backspace, just do a bit of editing, and then hit equals again. That's the best bang for your buck. So the first one is going to be negative 6.67, scientific notation, negative 11, times 5, oh, negative 11 didn't show up, times 5.98, scientific notation, 24, times 1200, divided by bracket 1.2, scientific notation, 7, plus 6.38, scientific notation, 6. I'm going to get a negative answer. You get negative 2.6041358 times 10 to the... I'll go to... you know what? Actually, the 3 looks like a good place to round off because there's a 0 right next to it. So I'm going to go negative 2.60413 times 10 to the 10th. 60413. Just as a rule of thumb, so you can tell if you've done this right or wrong, usually when you're figuring out how much energy, potential energy, objects have when they're in an orbital height, even if they're not in orbit yet, it'll be in the 10 to the 9th, 10 to the 10th range. Once in a while, 10 to the 11th, if I put something way out there, then I'm going to backspace. Have you figured out how to backspace on yours? You can. We'll have to look at the manual somewhere. So sadly, right now, you're going to have to retype this whole thing. I feel for you. I told you to get a good... Okay. The negative I delete, And I guess all I need to do is delete the 1.2 times 10 to the 7th. And my second term is positive 7.5022 times 10 to the 10th. Yes? No? Lorenzo, yeah? You sounded so confident. You made a typo, probably. You're good? Yeah. I think you're lying, but that's okay. By the way, to put something up there, will it actually take energy? Yes. Will I do work? Yes. I should get a positive answer. Let's find out. So I'm going to go negative 2.60413, scientific notation 10 plus answer button. Did I get a positive answer? And it was in the 10 to the 10th range, which it often is. 10 to the 9th, 10 to the 11th. 4.90 times 10 to the 10th. That's how many joules of energy, and if you knew how many joules per liter your rocket fuel gave you, this would tell you how much rocket fuel you needed. By the way, you haven't put the satellite in orbit yet. You just got it to the correct height. Now you need to give it some kinetic energy. Justin, this number here, fairly big? This is why putting things in orbit is ridiculously expensive. I think right now it's about $30,000 a pound. People like Elon Musk and Jeff Bezos from Amazon, they're trying to make space parts reusable. They're hoping to get it down to about $5,000 to $10,000 per pound. Right now at $30,000 per pound, countries can have satellites and large multinational billion-dollar corporations can have satellites. Those are the only ones that can afford it. If they could get it down to about $5,000 per pound, probably most big universities could afford a satellite, and most big towns like Vancouver could afford their own communication satellite. Maybe even a place like Surrey or Burnaby. Pitt Meadows, sorry, still no. But, you know, towns that had 600,000 or 700,000 could probably afford to launch their own communication satellite if they felt like it, or their own weather satellite or whatever. But it's crazy expensive, and it's even worse. Of course, since this satellite has no kinetic energy, it will simply fall back down to the Earth. So to lift an object, we only need to give it, to keep it in a stable orbit, we need to give the object both potential and what type of energy? Let's figure out how much work that takes. And spoiler alert, it's a lot of work. Mr. Dueck, we just did example 2. How come this is example 2? Shut up. Call this example 3. I like example 3. I like example 3. I like example 3. Example 3 is a nice question. Gabe, what's example 3 asking me to find? How much what? Okay, so just as before, except I see the word orbit, orbit, and orbital speed. Sadly, the kinetic is not going to be 0. The change in kinetic is not going to be 0. So I'm going to start out exactly the same way. Work equals change in potential plus change in kinetic. I don't advise doing all this at once. Gabe, I'm either going to find the change in potential or the change in kinetic first. Pick, doesn't matter. Which one would you like to figure out first? Potential. So I often draw a little line. And now I'm going to go, okay, change in potential. And that's going to be what's change in anything? Final minus initial, negative, big G, big M, little m, all over our final minus negative, big G, big M, little m, all over our initial. The change in potential energy is going to be negative, okay, big G.
Negative 6,767 times 10 to negative 1.
Big M. Little m, 925? Yes? And then our final. That 2.6 times 10 to the 7th, Gabe, is it meters? This number right here, is it in meters?
Yes.
Yay, so no conversion. Is it an altitude or is it a radius? So I don't need to add the radius of the Earth. I actually gave you that distance in the question. So, yay! A little less typing. I'm just going to put 2.6 times 10 to the 7th. Gabe, what's a minus minus?
Positive.
Are you positive? And then I'm going to argue, Gabe, same thing times same thing times same thing over. And again, this lets you fit this into one line. Maybe some of you write smaller than me and could fit it into one line regardless, but I just can't. Our initial, we started out on the surface of the Earth, so 6.38 times 10 to the 6th. Most of us can backspace and edit. So I'm going to do these one term at a time. Whew. Oh, I don't know. Some of your calculators, you might be able to go back more than one line. If you can, see, I notice that I'm often typing negative 6.67 times 10 and times 5.98. So I'm actually going to just keep going back in my work until, oh, there's a 6.67 and a 5.98. All I need to do is stick a negative in front of it and then type over the rest of the numbers. So instead of times 1200 times 925 divided by 2.6 times 10 to the 7th, delete the rest. That's a win. And I got for PE final negative 1.419 times 10 to the 10th? Or am I wrong? I see a nod? Yeah. And that 9 is a good place to round off. That's including the 0, 5 sig figs. So negative 1.4190 times 10 to the 10th. I smile because Mr. Dueck said that the energies are often in the 10 to the 9th, 10 to the 10th range. So Ethan, I probably did this right. Plus, ditch the negative, change the denominator, 6.38 times 10 to this. You have blisters on your thumbs yet? 5.7829 times 10 to the 10th. Can I get a confirmation from someone else? Yeah, 5.7829. So what is the change in potential energy? It's negative 1.419 times 10 to the 10th plus answer button. Haha. And I get positive 4.3639 times 10 to the 10th. Anybody else? We may be different on the last few sig figs depending on what you rounded off to, but 4.3639 times 4.3639 times 10 to the 10th joules. I tend to put a box around this because I'm going to come looking for it later, and you're going to find some of these questions take the most work. Take a whole page. There's my change in potential. Well, Gabe, what other change in do I need to find? Now, again, if we were just lifting, we would assume that we started at rest and ended at rest. Yay! What's change in anything? A half m v final squared minus a half m v initial squared. V final squared would be v orb. Now, I gave you the orbital speed. If I wanted to make this even longer, I wouldn't have given you that. If you know the orbital radius, can you figure out the orbital speed? Gravity is what's pulling me in a circle. V orb equals the square root of, I think it was big G, big M over R, but I'd have to derive it. You could actually have calculated this. I did it for you, but for what it's worth, that would be yet one more step. Is my initial speed 0? Well, it depends. You could say, well, we're starting out on the Earth at rest. And I would say, yeah, except now we're going cosmic. Is the Earth at rest? It's spinning. Where is it spinning the fastest? On the equator. On the equator. Believe it or not, we always launch in the same direction as the Earth's rotation for that speed boost. And the further south, the closer to the equator that you can launch, the better. This is why the Russians had such a tough time with their space program back in the 50s and 60s. They didn't have anywhere near the equator. They were launching from a further northern hemisphere. They didn't get the same speed boost. Where did the U.S. build their space launch center, by the way? Which state? Florida, as far south as possible, on purpose, to get that extra little space boost. The Russian rockets are workhorses. They're just engineering brute strength machines because they didn't get that space boost. And so the best place to launch would be along the equator. That's why Elon Musk and Jeff Bezos are trying to build ships that you can launch from, because they would say, why wouldn't you just launch from the ocean somewhere on the equator and get the biggest speed boost possible? So are we at rest? Technically not. But for me to figure out VI, I would need to know what latitude you were launching from. So we're going to assume that we are launching at rest. So where are we launching from?
North Pole.
We're launching from Santa's workshop or Superman's Fortress of Solitude at the North Pole. I don't think Santa has rockets. Superman might. So we're going to be launching always from Superman's Fortress of Solitude, just to keep the math nice. And then if we could launch further south, we would get a speed boost, but I'd need to know your latitude. If you're bored sometime, I can walk you through the calculation. It's medium complicated, but not crazy complicated. Me. Okay. Well, this isn't too bad. It's going to be 0.5 times 925 times 3,917 squared. You're going to find, to stay in orbit, the kinetic energy is often in the 10 to the 10th, 10 to the 9th range, but it will always be less than the potential energy change. .5 times 925 times 3,917 squared. You get 7.09608, 7.096 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. I went to 5 sig figs. I went 7.0961 times 10 to the 9th joules. That's the change in kinetic. I'm going to put a box around that. This is pretty near the single longest question you'll do all year. This is, and no pun intended, the most work you'll do on a single question. I realize we're finding work and getting big answers, but the only thing longer than this would be if I hadn't given you the orbital speed, if I made you calculate it. Gabe, what do we want to find at the very beginning? How much what? Which was the change in potential, 4.3639 times 10 to the 10th, plus the change in kinetic, 7.0961 times 10 to the 9th. Plus 4.3639 times 10 to the 10th, and I use my answer button for the change in kinetic. And I get 5.07 times 10 to the 10th joules. Final answer. So, is it tough to go into outer space? Does it take a lot of energy? It gets worse than that. It's actually worse than that. You see, now that you know how much energy you need to get this satellite in outer space, you could calculate how much fuel this is. And you know what just happened? Your mass just changed, because you'd have to now include the mass of the fuel. So that means that this number just got bigger, and this number just got bigger, which means that this number just got bigger, as did this number right here, which means this number just got bigger. So now you need to recalculate, uh-oh, the mass of the fuel just changed again. You need more fuel, which means that this number just got bigger, and this number just got bigger, and this number just got big. This is the rocket designer's dilemma. Mass is everything. Mass is everything. The lower mass, the better. Anytime, even a pound, even a kilogram of mass, oh my goodness, it changed everything. That's why there's no fat astronauts. Okay. I'm going to pause here. If you want to get a head start on the homework, I'm going to finish this off next class. You can certainly try number 1, and you can certainly try, actually skip number 1. You can do number 2, and you can try number 3. But I'd like to teach you how to build a Death Star.